Ready for a grid search that trips up even the best? Word search is a Pattern Mastery 100 classic and a go-to at Google, Amazon, and Microsoft for testing backtracking and matrix exploration skills. Over 35% of candidates make off by one or revisit bugs. If you can crack this, you're truly ready for matrix pathfinding in any interview. Let's break down word search with the basic approach, so you can confidently navigate tricky grids and recursion. Given a 2D grid of letters and a word, determine if the word exists in the grid. The word must be constructed from letters of sequentially adjacent cells, horizontally or vertically, and the same cell may not be used more than once. Input: 2D grid of characters, board. String word. Output: Boolean. True if word exists in the grid, false otherwise. Think about a mobile game where users swipe letters to form words. Your algorithm checks if a word can be formed with one continuous, legal swipe. An interviewer might ask, how would you design a feature for a crossword app to validate user input on the fly? What's tricky? Must track visited cells, can't revisit within a single search path. Need to try every possible starting point in the grid. Backtrack if a path doesn't lead to a solution. Loop through every cell in the grid. For each cell, use DFS, backtracking, to attempt to build the word. If the current cell matches the next letter, recursively check all four directions, up, down, left, right. Mark the cell as visited so it isn't reused in the current path. If you reach the end of the word, return true. If the path fails, backtrack, unmark the cell, and try other paths. If no path works, return false. Let's clarify. Use a temporary mark, like setting to hash, or a separate visited set to mark cells in the path. Restore the cell after recursion to allow reuse in other paths. Carefully handle boundaries to avoid index errors. Edge cases. Word longer than total grid cells, return false. Grid with only one cell. Grid with duplicate letters. Loop over each cell in the grid. For each cell, run DFS/backtrack. If out of bounds, wrong letter, or already visited, return false. If all letters matched, return true. Mark cell as visited. Recourse in four directions. Unmark cell after recursion. If any path returns true, the word exists. Now, let's break down the first Python solution for word search, a neat depth-first search with backtracking that checks whether we can trace the target word through the grid one letter at a time. We start by defining the solution class. This is the outer container where LeetCode will look for the exist function to run. This defines our main function, exist. It takes a board, a grid of letters, and a word, and answers a yes or no question. Can we trace this word on the board by moving up, down, left, or right? Here we grab the dimensions of the grid. M is the number of rows. N is the number of columns. We'll use these to stay inside the boundaries of the board. We create a 2D list called visited with the same size as the board. Each cell starts as false, meaning we haven't stepped on that cell yet. This helps us avoid reusing the same cell twice in a single path. Now we define a helper function DFS, short for depth first search. I and j are our current row and column on the board. K is the index of the character we're currently trying to match in the word. This checks if we've already matched all the characters in the word. If K has reached the word's length, that means we've successfully traced the entire word on the board. In that case, we return true to signal success. Here we handle all the bad situations in one line. If we go off the board, I or j out of bounds. Or if we try to reuse a cell we've already visited in this path. Or if the letter in the current cell doesn't match the kth character of the word, then this path is invalid. So if any of those conditions are true, we stop and say, this route does not form the word. Now we mark the current cell as visited, like placing a temporary footprint so we don't step on it again while exploring this path. This is where the exploring happens. From the current cell, we try moving in four directions. Down, I+1, j up, I, 1, j right, I, j+1, left, I, j, 1 for each move, we advance to the next character in the word, k+1. If any of these four recursive calls returns true, then res becomes true. Because we branch up to 4 ways at each character, this contributes to the time complexity of about om middle.n middle.4 to the power of k, in the worst case, where k is the word length. After exploring from this cell, we undo the footprint, we mark it as not visited again. This unmarking is the backtracking step. It allows other paths to reuse this cell later. We return whether any of the 4 directions led to a successful match of the word. Back in the main function, we start a loop over every row I of the board. And inside that, we loop over every column j. Together, These two loops visit every cell in the grid as a possible starting point. For each cell, we first check if its letter matches the first character of the word. If it does, we call DFS I, J, 0, to see if we can build the entire word starting from that cell. If DFS returns true, we found a valid path. In that case, we immediately return true, because we only need to find the word once somewhere on the board. If we finish checking all cells and none of them can form the word, we return false. That means the word does not exist on the board. And that's how this algorithm works. It first sets up tracking for visited cells and a DFS helper, then tries to build the word starting from each cell, exploring in all four directions with backtracking. Efficient, simple, and elegant. Test case check. Let's walk through it. Input board equals A, B, C, E, S, F, C, S, A, D, E, E. Word equals A, B, C, C, E, D. Let's test our function using this 2D board of letters and the target word A, B, C, C, E, D. The board represents a grid where we can move up, down, left, or right, and the challenge is to determine whether we can trace the word by moving through adjacent cells without reusing any cell. Quick logic check. To form the word A, B, C, C, E, D, start at the top left. The first letter A matches. Move right to B. Move right again to C. Then move down to the next C. Move left to E. Move down to D. Every letter is found in order, and each cell is used only once, a valid continuous path. Output true. And that's exactly what our program outputs, true. This matches the expected result, confirming that the depth-first search logic is correctly exploring all valid paths. So, our implementation is correct. The algorithm successfully navigates the grid, checking each path efficiently, accurate, thorough, and fully validated by the test case. We begin by defining the solution class, the structure where LeetCode will look for our exist method. This declares our main function. It receives a grid of letters, board, and a target string, word, that we need to locate by moving up, down, left, or right. We check whether the board is empty or invalid. If so, there's no way to find any word. In that case, we immediately return false. We store the grid's dimensions. M rows. N columns will use these values to stay within the boundaries of the board. Now we define a helper function called DFS, short for depth first search. This is where the real exploration happens. We check whether word K can be matched starting from cell I, J. If K has reached the length of the word, that means we matched every character successfully. So we return true to signal that the word has been found. This line blocks invalid moves. Moving outside the board, or stepping on a cell whose letter doesn't match what we need at position K. If any of those conditions fail, this path cannot form the word. We temporarily store the current cell's letter so we can restore it later. We mark this cell as visited by overwriting it with a placeholder. This prevents revisiting the same cell during the current search path. This line explores four possible directions from I, J, down, up, right, and left. If any direction returns true, then the word continues correctly in that path. This branching leads to the worst-case time complexity of OMN middle.4k. After exploring, we restore the original character. This is the key backtracking step that makes the board reusable for other starting positions. We return whether any of the four directions successfully match the entire word. We now loop through all rows of the board. And for each row, we loop through all columns, checking every cell as a potential starting point. For each cell, we attempt to match the word starting at index 0. If any DFS call returns true, we're done. If any path yields success, we return true immediately. If we finish scanning the entire grid without finding the word, we return false. And that's how this algorithm works. It first checks that the board is valid, then uses depth-first search with in-place marking to explore all possible paths for the word. Efficient, simple, and elegant. Let's test our function using this input. Board equals A, B, C, E, S, F, C, S, A, D, E, E, and word equals C. This 2D array represents a letter grid, and our goal is to check whether we can trace the word C by moving horizontally or vertically through adjacent cells. Quick logic check. Here's why the solution works. We're trying to see if the word C can be found in order on the board. For example, we can start at the second row, last column where we find an S. From there, we move down to the third row, last column which contains E. Then, we move left to the cell right next to it, another E. This gives us the exact sequence SEE without revisiting cells, which satisfies the word search rules. And that's exactly what our program outputs, true. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully finds the target word by exploring valid paths in the grid, efficient, accurate, and reliable. Let's wrap it up. The word search problem is one of those interview classics that blends logic, recursion, and precision. It's the ultimate test of how well you handle grid traversal without getting lost in the details, or revisiting the same cell twice. We began by understanding the challenge. Given a grid of letters and a word, we need to check if that word can be formed by moving through adjacent cells, horizontally or vertically, without reusing any cell along the way. It's about exploring every valid path to see if the word can be built in sequence. We compared approaches and quickly saw that brute force isn't practical. Checking every possible path without structure would explode in complexity. The elegant solution is backtracking with depth-first search, trying each starting point and exploring all possible directions while marking visited cells to avoid repeats. Our plan was clear. Loop through each cell in the grid, start a DFS whenever the first letter matches, move recursively in all 4 directions, mark cells as visited during the search, and backtrack afterward. If we ever reach the end of the word, we know it exists in the grid. We implemented the DFS with careful boundary checks and visited tracking, ran it on LeetCode, and everything executed flawlessly, no errors, no infinite loops. After testing across multiple grids and edge cases, every run produced the expected results, confirming that our backtracking approach is both correct and efficient. The takeaway? Backtracking isn't just about recursion, it's about control. Knowing when to explore, when to back out, and how to track state cleanly is what makes this pattern so powerful. Master this, and any matrix or pathfinding problem will start to feel like second nature.